Hi, this is Alex from devstories.eu. OpenCV Computer Vision Deep Dive, Episode 4 of 20. The most robust visual trackers do not memorize what an entire object looks like. Instead, they lock on to mathematically distinct corners and high-contrast gradients that stay consistent regardless of the lighting. Getting this right is the domain of feature detectors, keypoints, and neural matching. Before we look at the mechanics, we need to separate this from object detection. Object detection applies broad semantic categories. It draws a bounding box and tells you that a building is in the frame. Feature matching is strictly structural. It does not know what a building is. It finds a specific identical intersection of two bricks across two different images. Think about building a panorama stitching application. You have two overlapping photos of a brick wall taken from slightly different angles. To stitch them seamlessly, the software needs to mathematically align the overlap. It does this by finding distinct local features in the first image, finding those same features in the second image, and pairing them up. The first step is detection. The system scans the image for keypoints. A keypoint is a specific pixel location that stands out from its surroundings. Flat areas like a clear sky or a blank white wall are useless because every pixel looks exactly the same. The algorithm hunts for high texture, sharp corners, and intersecting lines. Traditionally, algorithms relied on handcrafted mathematical formulas to find these edges. Modern approaches use convolutional neural networks. You feed the image into the network, and it outputs a probability map indicating how likely it is that any given pixel is a stable keypoint. Once the network identifies a point, like the corner of a specific window frame, it needs a way to describe it. This is the descriptor. The neural network generates a high-dimensional vector and embedding that captures the visual pattern of the pixels immediately surrounding that keypoint. A robust descriptor remains mathematically similar even if the second photo is taken at a different scale, rotated, or under different lighting conditions. Here is the key insight. Having a list of points in their descriptions is only half the puzzle. You still have to match the points from your first image to the points in your second image. Historically, you would just calculate the distance between the vectors and pick the closest one. But repeated patterns, like hundreds of identical bricks on a wall, cause severe mismatching errors. This is where neural matching models come in. Instead of evaluating one key point in isolation, a neural matcher looks at the spatial relationships between all the key points at once. It essentially learns that a specific corner might look like 50 other brick corners, but it is the only one located exactly between a window frame and a specific shadow. By passing the descriptors and their geometric positions through self-attention layers, the system rejects false positives and outputs highly accurate matching pairs. In a typical pipeline, you first pass both images through a feature extraction network. This returns two sets of keypoints and two sets of descriptors. Next, you pass both sets of data into a matching network. The matching network computes the contextual similarities and returns a list of valid pairs, throwing away the keypoints that do not exist in both frames. You then use those matched coordinate pairs to calculate the geometric transformation needed to warp and stitch the two photos perfectly together. The shift from handcrafted formulas to neural embeddings means feature matching can now handle extreme variations in lighting and extreme viewpoints that used to completely break older algorithms. Thanks for listening. Happy coding, everyone.